Hello, my name is Nathalie Bouet. I'm part of the Optics and Metrology group at NSLS-II. My presentation today is about imaging the nanoworld with X-rays, or more exactly, how do we do that? This is a very ambitious title, but what I'm really trying to do here is to explain you a bit more about what we are doing in our group and our impact on NSLS-II. In particular, I'm going to focus my presentation on what we do for the HXN beamline that offers our users the highest spatial resolution for imaging their sample. And that spatial resolution is about 12 nanometer at 12 keV. Simplifying things, HXN is a very fancy microscope that users can use to look at their sample, enabling discoveries in many fields. Here I put a few examples on the fields of microelectronics, biology, or even looking at new materials, emerging technology such as DNA and gold particle-based materials. If you want more insight, I encourage you to look at our website or at the HXN page for the science highlights. So, why offering high spatial resolution matters? Well, the higher the spatial resolution, the more detail scientists can see on their sample. At an age where a lot of developments are happening at the nanoscale, it is more crucial than ever for us to be able to deliver such beams to our users. As you can see in these images, if you have a microscope for which the resolution is not so good, you're able to kind of distinguish some colored dots, but you cannot figure out what is the image about. As the resolution improves as you go towards the right, you can see more and more details. And as you see these details, you can now make up that these are cars on a parking lot. So at the beamline, to take images, we have a source of light, a set of optics, and then an end station when users are loading their samples to look at. Similarly to the game that you have on the right, what my group is doing is trying to help the beamline scientists manipulate the light from the source and bring it to the sample. I put on the left the sketch of the HXN beamline I showed you before, and you will see a group of optics that are situated very close to the sample. These are the optics that are really bringing this very tiny high resolution to the beamline. So what I'm going to try to explain you is what are these optics and why the optics we are using are not your traditional mirror. They are not the optics you are able to find, or mirror you are able to find at Marshalls or Home Goods, and they are in fact very different. X-ray optics are often based on silicon, and to make them usable, we often have to add thin films on it or multi-layer films to be able to interact with the X-ray and to manipulate the light. I put on the slide a few examples of them on the right. They vary in size for a few hundreds of microns, like you can see at the bottom, and they go up to a few tenths of centimeters. Putting things in perspective, they are any size between the size of a fifth of a sand grain to the size of a bowling pin. And so in the case of HXN, it gets even more special because we want to focus the light to this very, very small spot. As I said, the spatial resolution at HXN is about 12 nanometer. And so to do that, we have to build these fancy optics that are based on thousands of layers that are deposited on a silicon substrate. The layers in our case are made of two different materials, silicon and tungsten silicide. To focus the beam to these tiny, tiny spots, the layer thicknesses need to follow a special rule. They need to be graded from the top to the bottom, from thicker to thinner, and each individual layer needs to be of a particular thickness. To give you a bit of a sense of what these optics look like in reality, I put a SEM image on the side. As you can see from looking at the scale bar, these optics are very, very small. They are about the size of a human hair. So we are building these optics one layer at a time. And what we are doing in our R&D labs at Building 703 is to take silicon substrate that we introduce into a very large deposition chamber. Once the substrates are loaded into the chamber, the substrates are going to pass in front of sources which are basically spraying atoms onto it. As the substrate is going to pass, it's going to be a bit like sugar dusting. If as we control the speed of at which we pass the substrate in front of the guns, we are going to be able to control the amount of material we are depositing. And what I'm going to show you is on a video that is going to start. You will see this purple colored beam, which is in fact made of atoms being deposited on the substrates that you see coming back and forth from the screen. So we are building these optics one layer at a time with this gradient. I put here some real SEM images of multi-layers that we have built, where you can see the extent of the film being about 60 microns in that case, with layers starting at 25 nanometer at the top and being about 20 times smaller at the bottom. So, as I said before, we need to very carefully control the thickness of each layer. But we also need to control what is the total thickness of the stack. And basically, we have to make sure that if we were building the Empire State Building, our tolerance is the size of a penny. So that's the level of accuracy we are looking for. And after having deposited all these layers, to make the optics usable at the beamline, we not only have to have this perfect film, multi-layer film, but we need also to cut a slice of that cake. And this slice has to be perfect to be able to focus the X-ray. So we need to find a way, find the right knife, if you want, to cut that cake, making sure that we are not going to have any deformation of the layers, making sure that we will not have any smearing between the layers, making sure we will not create any bending, and not only we are cutting this slice, but this slice needs to be perfectly straight. And we need to find a way to manipulate it, to handle it. And so we need to go over all these to really deliver the optic to the beamline. So to do that, we use a mix of old and new technology. Here you have a picture of Juanzu, who is working with our group, and she's doing polishing of the film. This is a very well-known technique, very versatile, used for a lot of material. You start with your blank material, and you polish it with diamond particles to thin it down. It has been used for a very long time, but in our case, it has a lot of drawback. And one is because of the multi-layer structure of our materials. In fact, this was evidenced by the first team that started to work on multi-layer Laue lenses on this type of optics. It's a bit like if you have a book and you try to polish the side, you will have splitting between the different pages. So it's exactly the same thing happening for us. So to try to solve this issue, we have been working with adding to that technology the use of focused ion beam. And this allows us to create some reinforcement on the side of the optics. So instead of thinning down to a very few microns, now you can live with a very large structure, and you are just going to do some milling of your very thin window using an ion beam instead of a laser. And so we are doing this using some facilities that exist at CFN, and we have a lot of interaction with them. So to give a sense of sizes, The optics I'm talking about, they start about the size of a quarter, but when it reaches the beamline, it's really the size of a human hair. You can see on this real picture of the optics that they are about 100 micron wide, 5 to 10 micron thick, and a few millimeter high. So it's very important for us to keep in mind the dimensions of these. So while HXN is leading the spatial resolution that it offers to our user, we are continuing to push the spatial resolution even further to enable new and even more science. And so to be able to do that, we are presently working on developing slightly different type of optics that are called wedge MLLs. And where not only we have to create these very precise layers, this very precise film, with the depth grading, but now we also need to introduce another gradient going laterally, and while keeping all the other things perfect. There is several ways of doing that have been proposed over the year, and this is a development that is still in progress. And with this, I would like to acknowledge all the people who are working with us on MLS R&D, all the optics and metrology group, and in particular, Dranzo and Stefano Giorgio that are working with my team, as well as the people of HXN and FXI and our collaborators at CFN. And with this, I want to thank you.